In the lectures, we have discussed so far the role of radiation heat transfer in gases, but we have treated radiation in isolation. But in real problems, radiation occurs along with conduction and convection. So, we need to look at problems where more than one mode of heat transfer occurs together. So, today we will look at radiation along with conduction heat transfer. This is the simplest extension of the pure radiation problem we had encountered so far. And the simplest problem we can do is assume a gray gas, one dimensional, to illustrate the manner in which radiation interacts with conduction. So, the simplest balance is conduction along with radiation, where z is your vertical coordinate and we have two parallel plates distance d apart with a gas here, which has both radiation and conduction heat transfer. And it would be convenient to redefine our z coordinate in non-dimensional z coordinate. You non-dimensionalize z as a into z. So, that becomes a z tilde, which is now non-dimensional. If you do that, the above equation becomes k a d squared d by d z tilde squared is equal to d q r d z tilde. And if you want to further proceed, we need to now write down the divergence of radiative flux in terms of the integral equations that we had developed earlier. Now, if you expand this term and write this down in terms of all the terms in the equation, the first term of course is the conduction term, it is already there, nothing new. And then we have the surface emission from the lower surface absorbed by the gas. Then you have the emission from the upper surface and we defined the Z0, which we will define now. So, Z0 is nothing but A into D, that is, you might call it as the total optical depth, measure of the highest non-dimensional optical depth in your example, and then you have twice 0 to z tilde sigma t to the power of 4 Z star E1 of Z tilde minus Z star dz star, and the next term twice Z tilde to Z0 So, just to remind you what these are telling us, this is the conduction heat transfer, this is the radiation which is absorbed from the emission by the bottom surface, the next term is the radiation absorbed from the emission at the top surface. Third term is radiation emitted by the layers of gas between 0 and Z tilde, and for convenience let us identify this in our this 0, this is Z tilde, this is Z0. Okay. And this is surface 1 and surface 2, and reminding you that both the surfaces have unit emissivity. So, they are black surfaces, that is what makes this problem somewhat simpler, and this term is the radiation emitted by this layer, and this is the radiation emitted by this layer. So, both these are to be understood in terms of. So, there is first term coming from here, absorbed here, second term starting from here, absorbed here, the third one is this one, and the fourth one is this one. That is what you are trying to balance at the level Z tilde. Now, to proceed further, it will be good to non-dimensionalize the equations, because it enables us to extract important parameters, because ultimately this equation has to be solved on the computer. If you are going to solve on the computer, you would like to keep the number of independent parameters you have to vary to bare minimum. Right now, for example, one parameter we have is of course AD, non-dimensional parameter. Then you are seeing Ka, the parameter coming in here. We have T1, we have T2. So, if you were to solve this problem numerically, we will have to solve it for various values of AD, which is our Z0. Okay. So, you have to vary Z0 over a range, then you have to vary Ka, you have to vary T1, you have to vary T2. So, let us say you are interested in solving for 10 different Z0s, 10 values of Ka, 10 values of T1, 10 T2, then you can see that you have to solve the problem about 10,000 times. So, in spite of the large computing power you might have, this is a lot of exercise, and not only it will take time to solve so many cases, then you have the challenge of interpreting the information in a suitable way. So, it is smart to look upon ways to non-dimensionalize the equations right here, so that you reduce the number of parameters you need to vary. Now, you have 4 parameters, let us see whether we can reduce it to 1 or 2. If you can do that, then life becomes much easier. So, if you look carefully, you can see that if a non-dimensional temperature as T by T1, you can do it various ways, but this is one of the ways. then you will have two parameters coming out of this analysis. One is the ratio of T to Tt1, let us call it theta 2, and conduction radiation parameter this for is a matter of convenience, it is not really needed, but you can use it. Now, this parameter is very important. This is just a ratio of temperatures. This parameter is very important because n is much less than 1, conduction is unimportant. Conductivity is so small that if n is much greater than 1, conduction is important. So, even before solving the actual problem, you will get a rough and ready idea of whether conduction is going to play a very important role in this problem. So, this is a very good measure. For example, let us take a gas like air, whose conductivity is of the order of 0.025 watts per square degree Kelvin. Let us assume that the absorption coefficient for air containing, let us say, carbon dioxide, water vapor, methane and so on, let us say an average value is 10 meter minus 1. This is just an example, not taken seriously. And let us say you are looking at a phenomena at room temperature, around room temperature, given let us say 300 K. This we know is 5.67 by 8 watts per meter squared Kelvin to the power of 4. Okay. So, this will give you n value of the order of 0.25, okay, 4 into 5.67 to the power of minus 8 into T1 cube, this will be 27 to the power of 6. Okay. Now, this will roughly come out to be 10 to the minus 2 here, goes up 2.5, about 20, so 1/10. This is fairly small. So, what we see very interestingly that even at room temperature, for a gas like air, the chances that conduction will be important is not very large. Okay. But however, if you were to take an example of a gas at a much lower temperature, and let us say T1, you are looking at cryogenic application for example, T1 could be of the order of 100 degrees Kelvin, then conduction can become very important. But at room temperature for gases, unless it is a highly absorbing gas like pure carbon dioxide or pure water vapor, in which case this quantity can be much larger, this simple analysis shows that conduction may not be very important vis-a-vis radiation. Now, let us write down the complete after non-complete equation. After non-nebulization, this whole equation will look like n d squared theta d z tilde squared is equal to 10 to the power of 4 a function of z tilde minus half E2 So, we see this equation now is much more easier to use because of the non-dimensionalization that has been done. Now, here I am writing a compact form of the integral term, which contains both the terms that we wrote down in the previous expression. This is a modulus here. So, you must remember that in actually solving the equation numerically, you have to expand this from 0 to z tilde to z 0, but here we have written it for convenience in a single expression. This is a matter of compactness for use. Now, this problem has to be solved on the computer. There is no other way, because of the as soon as in say conduction radiation interaction, radiation goes as t to the power of 4, conduction goes linearly in t. So, when you combine the two, you are going to have problem of nonlinearity. The problem is nonlinear. Hence, the only way you can solve this is numerically, and I will give some results from the numerical solution to give you a flavor of how conduction influences radiation. So, we have two main parameters z 0 and n, which is the ratio of conduction to radiation. We also have a third parameter, which is theta 2, which is T 2 by T 1. So, we will not worry about this so much. Now, let us look at a typical example of how the radiation heat transfer from plate 1 to plate 2 is influenced by variation of n. So, let us take z 0 of 0.1, this is a fairly non-absorbing gas, and let us look at two values of n, 0 and 10. 0 is a case where conduction is not there at all. So, what is the value of q by sigma T 1 to the power of 4? Okay. So, if there is no conduction, this value will come out to be around 0.86. When there is conduction dominating in a big way, this can be 200.88. So, what you see clearly here, that if value of n in this example was of the order of 10, that is conduction is of the order of 10 times larger than radiation, then the heat transfer rate from the surface of the bottom plate almost goes up more than 200 times. So, you can see that although we found that in many cases n is quite small, but if you think of a cryogenic application where T 1 is very small, then it is possible that this quantity can go about 10. Notice that this quantity can go about 10 also if A is much greater than 1. That is, the absorption coefficient is much larger, then also n becomes large. Okay. So, either conductivity is very large or the absorption coefficient of the gas is very large. One of the two leads to n being very large. And the next important thing which we want to illustrate is, this is for the small path length. Now, if you go to a large path length limit, let us take Z0 of the order of 10 and consider no conduction case, in which case you will get this quantity to be around 0.102, while n equal to 10 will take you to 2.114. Again, going from n equals 0 to 10, the heat flux does increase, but notice that the increase is only about 20 times. In the previous case, it was 200 times. So, the overall optical depth in the medium has a role to play. The other thing you must remember is the nature of the temperature profile, that is to be remembered. Now, we will plot this in terms of T by T1. T by T1 maximum value you can reach is 1, and we have taken theta 2 to be T2 by T1 of the order of 0.1, that is somewhere here, and this is Z by Z0, which has to go between 0 and 1. Now, if you look at this problem in a pure conduction domain, then you will get a linear profile of pure conduction. However, when we have radiation, as you recall from our previous discussion, there is a slip. So, temperature profile will look like this and will go like that. Okay. So, we will have a sharp change here, which is called the slip at both walls, and it represents the fact that when there is radiation heat transfer, there is no guarantee that the temperature of the gas near the wall has to be equal to wall temperature. But of course, since we have included conduction here, conduction heat transfer will ensure the continuity of the profile near the wall, but that layer over which this will occur can be quite thin, and it will almost look like an abrupt change. So, this simple model illustrates the interaction between conduction and radiation, and we found that essentially it is a 2 parameter problem, one involving the optical depth AD and the other involving the conduction radiation parameter Ka by O sigma T1 cube. Now, if you look at this parameter, you can see that the temperature of the surface does play a role. That is quite understandable because of the fact that radiation heat transfer goes as 4th power of temperature. Higher this value, more important is radiation compared to conduction. The second part, of course, is the molecular conductivity of the gas. That, of course, will make conduction more important if K is large, but the role of the absorption coefficient is slightly counterintuitive, because you would have thought that a gas in which the absorption coefficient is large will be the one where conduction is less important. Okay. But you need to be really careful here, because the absorption coefficient plays 2 roles in this problem. It comes in this parameter, it also comes in this parameter. So, when absorption coefficient plays a role through 2 independent parameters of the problem, you cannot make any judgment based on looking at only one. Suppose you increase A here, of course, N goes up. So, conduction is more important, but A is also increasing here. Okay. So, if you look at the results we have looked at so far, if we keep N constant, let us say N equals 10, that is conduction is important, and your Z0 goes from 0.1 to 10, then we saw our heat flux went down. Okay. By a factor of 100. So, although conduction is dominating according to N value, the role of radiation also comes through the value of Z0, and as you increase the value of, so in this case the way to interpret the result is that if you take a gas in which A is fixed, but Z0 is going up because the dimension of the problem has gone up, the D has increased. So, what it says is that if you have a thicker layer of gas, the heat flux will go down, and that is absolutely understandable. Okay. So, changes in Z0 and N can be interpreted smartly as long as the same parameter does not appear in both these terms. So, that is the issue here. If it appears in only one of them, then we have no problem in interpreting the result, but if it appears in both, then you are a little careful about how you interpret the result. Now, we will get some more insight into these interaction problems by looking at now radiation and its interaction with convection. Now, this is a more complicated problem than conduction, as you might recognize, because we are talking about a fluid flow problem really. So, you need to address the issue a little more carefully than the conduction problem we did, but we can still do the problem in a very simple context by assuming flow over a plate, and since our aim is to primarily understand the role of convection in a qualitative way, we look at the simplest problem in convection, when we assume that the fluid flowing over the plate has a single velocity equal to u infinity. That is, this is what you might call as ideal fluid flow. We are neglecting the role of the boundary layer. That is, the boundary layer near the wall has been ignored. Essentially, all of you know that if you plot u with height above this one, the normal profile is something like that. Okay, this is u infinity. So, what we are doing is we are replacing that by an ideal profile, this one. So, this is a real profile, this is ideal profile. An ideal profile ignores the fact that right close to the wall the velocity has to go to 0. We will, so this is an approximation. It is not essential to make the approximation, but it does make it somewhat easier to interpret the results if we look at this ideal fluid case first. Okay. Now, if you do that, then your advantage that we have, let us call this direction as x and the direction as y. Now, we can write down the simple equation as heat removal by convection by fluid flow is equal to minus 1 over rho C p delta q r delta y. So, this is the simplest problem you can solve in the context of convection radiation interaction. We cannot think of anything simpler than that. And once it provides us some insight, we can proceed to more ambitious models with more terms of the equation. Now, further we will take up a case where this problem is linearized. Now, we saw that if we do not linearize the radiative transfer equation, the problem becomes highly nonlinear and interpretation also is difficult. So, we would like to know that if you write down the equation in linear terms, whether the problem is more tractable. So, what we do is we replace T to the power of 4, which keeps coming in the radiation problem, as approximated by the temperature at infinity plus this is essentially a simple expansion of T to the power of 4 around t infinity to the power of 4, that is all it is. The simple Taylor series expansion. Essentially, you are saying t to the power of 4 is what is the wall and the derivative of the t to the power of 4 in terms of 4 sigma t cube kind of term into t minus t infinity. Okay. So, the simple way of Taylor expansion of t to the power of 4. Okay. So, once you linearize the equation, and then of course, we again want to non-dimensionalize to make life easy in terms of the wall temperature and the temperature at infinity. So, you have the plate, you have temperature infinity, temperature of the wall, this is our x coordinate and this is our y coordinate. And that is a non-dimensional temperature. And if all the needs is done properly, then the equation can be rewritten. So, the old dimensional equation was this, and this can be converted to a non-dimensional equation as delta theta delta psi. We will define psi right now, 4 0 to infinity theta into E1 of mod tau minus t dt minus 8 theta. So, this has come about because of the non-dimensional linearization that we have done. In this, we have two parameters, one is tau, which is the optical depth, non-dimensional in terms of A and Y. A is the absorbed quotient of the gas, and psi is the non-dimensional x scale there is a non-dimensional x coordinate and tau is the non-dimensional y coordinate. Okay. And the only boundary condition we have is that at x equals 0, the beginning somewhere here, theta at x equals 0 and any theta at x equals 0, the location at any tau location has to be equal to 1, because that is the initial starting of your. Now, you can solve this problem analytically by various interesting approximations, and one of the approximations you can do is to do a series expansion. So, we will give that result first to show you how that result looks like, and later we will do more elaborate calculations. So, first example is what is called the series solutions. In a series solution, you expand the temperature profile, which depends on x coordinate and the y coordinate, in terms of the value at psi equals 0, which is equal to 1, and hope that you can expand this in the following form. So, you are expanding the non-dimensional temperature in terms of the two functions psi and tau, and psi, remember, is your x coordinate and tau is your y coordinate. So, as you probably realize, this is a solution which will only work for small psi, because there is a series expansion. We wanted to converge, we will converge only if psi is less than 1. Okay. Although you might think this is a very limited approach, you must remember that even if you were to solve this equation in the computer, you will have some difficulty close to the origin, because of some unusual behavior of these functions near the origin of this system. So, even when you are solving this part numerically, you will find it very convenient to have some good approximate solutions near psi equals 0, which you can use as an input to your more complicated numerical solutions. So, even in these days when powerful computers can be used to solve complex problems, even in such cases it is useful to have approximate analytical solution, which may be a good starting point or good guessing solution in an iterative technique or some other technique. So, many of the techniques that we adopt today, numerical technique, depends on a good initial guess, and the good initial guess either comes from your intuition or it comes through your ability to generate this kind of solution. Okay. So, although it is a limited solution, so now you substitute this into the equation, this equation, okay, and you collect like powers of psi. That is, you match on the other side of the equation terms containing the same power of psi, because they have to match, otherwise solution is not valid. And you do, they will get G1 of psi is equal to minus 4 E2 of tau, G2 of psi as 16 E2 of tau minus 8 and when you solve this equation at the origin, G1 of 0 will come out as minus 4 and G2 of 0 will come out as 12. Okay. This is to satisfy your boundary condition at psi equals 0. Okay. With that, you get the final solution for theta as 1 minus 4 of psi plus 12 psi squared, and other order terms if you can have the patience to calculate more higher order terms. And let us just remind ourselves what the solution looks like. So, T of psi and 0, now we are talking about the value at the surface of the plate minus T wall by T infinity T wall, finally has come out to 1 minus 4 psi plus 12 psi squared, and maybe some higher order terms which we do not know yet. Now, what is this saying is that at psi equals 0 it is 1, which is the requirement of the problem, and as psi increases the temperature will decrease. But notice that this is strictly valid only for small psi. So, let us take psi is 0.1 for example, then you will get 1 minus 0.4 minus 0.12 plus 0.12, right. This is 0.01. So, this shows that the temperature will decrease as you go, the non-dimensional temperature will decrease to about 0.72 at a distance of 0.1 from the origin. Now, very often in radiation problems, we are just not satisfied with the temperatures, we also want fluxes. In this case, the flux at the wall can be written as and flux is always non-dimensionalized by the flux that will exist in the absence of the gas, that is your measure, and this can be easily be shown to be theta of sin t E2 of t dt. Okay. So, now we know this solution can be substituted here and we can proceed further with the solution. When you do that, this is what the solution will get. So, Q r of 0 divided by okay. So, this is how the radiative flux non-dimensional value as the ratio of the flux without any gas will vary along the x axis. Again, notice this is valid only for psi much less than 1. So, again it takes psi as around 0.1. You can see that when there is a gas and there is convection playing a role, the radiated flux of the wall will reduce at small psi. We cannot say anything about large psi because this approach is not valid for large psi. So, we merely did this simplified analysis just to provide an insight into the nature of the problem. Now, it is good to move on to more ambitious approaches, and the one which has been very successful in our earlier examples of pure additive transfer has been the use of kernel approximation. So, you can ask why depend only on linear series solutions, why not go for kernel approximations. So, we will attempt a solution to the problem we had posed earlier in the context of kernel approximations. Okay. And the approximation we had earlier used was series solution. Now, the series solution has a problem with regard to the value of psi. It is valid only if psi is much less than 1. Now, that is an approximation which is not very useful if you want to go very far down. So, now we will look at extension of series solution by using more. Now, the equation you are trying to solve is this one, delta theta delta psi is equal to 4 0 to infinity theta E1 of tau minus t dt minus 8 theta. Okay. So, this equation we are trying to solve, and if you recall the typical kernel approximations one can think of, or one example of this is E1 of t is approximately equal to two e to the power of minus 2 t, and e to t approximately equal to e to the power of minus 2 t. Now, in this approximation what we have ensured is that e to t is satisfied exactly at t equals 0. At t equals 0, e to t is 1, which is the exact value. Well, E1 of t actually goes to very high value of t equals 0, but we have restricted it to value of 2. But remember, E1 of t appears inside the integral. So, it is not as important that we get the value of E1 correct at all locations, as long as we get the answer correct in the integral sense. Our approximation is not that bad. Now, with this approach, you can write down the non-dimensional change in temperature as equal to 8 e to the power of minus 2 tau 0 to tau. Now, we are expanding the integral theta e to the power of 2 t dt plus the second term tau to infinity. Now, we are going to we are assuming everything going up to infinity in the t direction here. Minus 8 theta, that is the last term, that does not change. So, this equation is a lot more complicated than we had attempted earlier. Now, the best way to solve this problem is by Laplace transform. and essentially we are going to transform the theta of psi and tau to theta of s and tau, where tau is the transformed where the psi coordinate is transformed to the s coordinate. Now, all of you recall that the Laplace transform definition just in is 0 to infinity theta of psi and tau e to the power of minus s psi d psi. So, we are transforming the non-dimensional theta from psi tau coordinate to s tau coordinate, where s is the transformation variable here. When you do that here and substitute into the equation, you will get the following equation: s plus 8 theta bar of s and tau minus 1, that is from the derivative term, and the left hand side will be essentially be same, nothing will change. Okay. And then when you apply the exponential approximation, we will discuss this in the how it is done in the next lecture.